start.
Alright, let's get started with.
चेक कर लेते हैं. आ रही है. ठीक है. Alright. So we covered schemas, scope, XFORM, and XFORM common API yesterday. And
Yeah,
today we'll just quickly go through lights and then we'll try to do the quiz, but no promises because I need to leave quick and because I need
same,
to pack
same.
as well. Yeah.
I think the most interesting.
Yeah, but just before we move to that, I am a little bit, I understood what the, goal for XFORM Common API was, but I just want to revisit the code once
Mm-hmm.
because I think there's like a little bit of blurriness over there.
Mm-hmm.
So real quick, we define the stage, we define the world prim, we define the
Mm-hmm.
parent prim, and
Mm-hmm.
then we make the parent translate rotate scale using the xform common api over here usdgm.xform common api parent, and we store that in a variable called parent xform api, and
Mm-hmm.
then we set the translate rotate and scale for parent xform common api because it is translating from one sec. नहीं नहीं वाले. Thank you. XFORM Common API, and then it's basically setting translate, rotate, and scale over here. And then the child translation is okay. Now, where did this child translation come from exactly? Like, how did they initiate this GFVec 3D without anything above?
Like, dude, that's that is the library that you're trying to import, and you can definitely initialize it as a 3D vector coordinate. As it said, like in if you go to Cloud Core, it's gonna show you it over there. It did said that why and how did we initialize it. Yeah, there we go. So okay, if you go up.
Oh, yeah.
Yeah,
Define a
define a
vector that
yeah.
says 2 units
First,
along X. This will be used for both children on purpose to show the punchline of the lesson analogy. You have a single instruction, hang 2 feet to the right of your parent that you're. But wait, 2 units along X. This will be used for both children on purpose to show the punchline of the child translation. Hang 2 feet to the right of your parent. Okay, got it. This is a mat type that from the graphics foundation library stands double precision, meaning it is a very accurate way to store coordinates. These are XYZ, X is 2, Y 0. Okay. Parent's location is 000. Okay. But how do we know that parent's location is 000?
with what? The parent location is 000.
Yeah, how do we know that?
The
If we are
parent location.
defining.
No, wait. So that's different, right? You remember yesterday we did discuss that if this is the parent and you bring a child onto this parent,
Hmm.
then the child will also inherit the same properties.
Yeah,
So
but
for
like there is no relation in how we are defining the relationship between this variable and this variable, right?
why do you need to define a relationship, dude? That's a
But
separate variable.
yeah,
You
but
can
like if we are defining a vec 3D at 2
yeah.
comma 0 comma 0, we're
Just
basically saying
assume
that you have to be 2 units on the x-axis from
yeah.
your parent position, right?
Yeah. So if
Okay,
you
oh, okay. Wait, I think I
you
understand.
see, like if you go in child A, you will see over there that how are you going to do that. So if you do parent dot get path over there, you are basically appending your child inside that, and
Parent
that's
dot
just
get path. Okay,
yeah. Now once you have appended your child, you're gonna apply those translation onto that child later on. You are not applying them right away. You are applying those translation once you have created your child prim.
mm-hmm.
So that is basically a variable that you're trying to pass. So even if you don't assign it over there and just copy this and pass it in the set translate as a parameter, it's still going to accept it. So what they have done is basically made it simpler for us to understand and reapply those translation again and again. You can also
Okay,
apply this.
wait. So wait. So when we are saying child translation GF vec 3D 2 comma 0
Yeah,
comma 0,
yeah.
right? We are just saying that there is an imaginary parent of this child that
Dude, don't
is
assume any imagine. Just assume that's a variable. You can change
okay.
it to x as well. X is equal to that thing. So you can say x is equal to 2 as well,
Okay.
right? So
Mm-hmm.
what you're trying to do over there is once you have created your child, focus
Mm-hmm.
on creating the child. Then look at where it is getting applied.
Okay.
First, you're creating the child A,
Okay.
and then putting the child A inside the parent.
Okay, so child A cone is USD geom
Yeah,
dot cone dot define stage parent
yeah.
dot get path. Now
Hmm.
parent dot get path, and then
So
parent is defined over here.
yeah,
The parent is
yeah,
okay here, and
yeah.
basically there is an XForm common API applied on the parent.
Hmm.
So that will be inherited by the child A cone as well,
Yeah,
and that child will be called child A,
yeah.
and then child A XForm API
Uh,
equals to
so now you're gonna
USD XForm API
apply that
child A cone. So we're gonna
API.
apply XForm common API to child A cone as well.
Yeah,
Okay.
so that we
And
can
then
perform the transformations and translations.
okay, so okay, now the parent prim plus transform. Oh, I get it. Parent prim transform plus local placement. So the parent prim transform is happening over here as well because it is
Yeah.
inheriting from the parent prim. And
Hmm.
then we are applying the XForm common API over here to the child AX form child
Yeah.
icon as well. So there is a local placement.
Yeah.
Got it. And then for
Yeah.
child B, this is an alternative parent which does not have the XForm common API, right? Which is called alt parent. And then we are doing the same thing. We are defining the cone. And but this time we are getting the parent from alt parent. And then we are applying the XForm common API just to the cone, like just to the child B. And then we are setting the translate over here. So only local placement. Got it. Oh, I understood the whole thing. Yes. Okay, I understood this. Yes. Got it. Lights. We can go to lights. My bad.
Yeah. Lights. All right, let's get started. And
In this
this
lesson,
lesson,
we'll explore lights in OpenUSD schemas belonging to USD Lux domain. Okay. Understanding the lights in OpenUSD allows for accurate, realistic lighting in 3D scenes. Let me play this. 2 minutes, 18 seconds. Okay, so directional dome, portal, cylinder, rectangular disc, and sphere. These are all light prims.
yeah,
Intensity and color. shade. Okay. Hmm. Okay. This is pretty basic. USD Lux is the schema domain that includes a set of light types and light related schemas. It provides a standardized way to represent various types of light, such as directional lights, USD Lux distant light. Okay, so this is the most basic one, USD
Yeah.
Lux distant light, which is directional. Area lights includes cylinder, rectangular, disc, and sphere, which is USD Lux cylinder, USD Lux rect light, USD Lux disc light, USD Lux sphere light. Pretty straightforward. And then dome lights and portal lights are USD Lux dome light and USD Lux portal light, respectively. Okay, how does it work? Start by defining light prims within USD scene. Okay, we define the sphere light like this, very straightforward, just like we define a normal prim. We are using USD Lux dot sphere light dot define. And then within a USD scene, these light primitives consist of scene description for specific light types. Example, USD Lux distant light for directional lights and contains attributes that provide comprehensive controls over the light's properties, such as intensity, color, and fall off. These light primitives allow for accurate lighting calculations during rendering. Working with Python, here are few relevant Python commands for working with USD lights. Import the USD Lux module from Pixar. Import USD Lux, USD Lux dot spherelight dot define part to light. Okay, light prim. Part to light prim dot get intensity attribute dot set 500. So we are setting the intensity to 500. All right. USD Lux has API schema that allows add light behavior to prims in your scene, so you can also add light properties to meshes and volumes. Got it. USD Lux is a USD lighting schema that provides a representation of lights. One of the schemas in USD Lux is distant light. Light is emitted from a distant source um, along the z-axis. This is commonly known as directional light. Okay, so let's do it in our notebook. Okay, we have already read this. So this is the first we are loading the relevant OpenUSD libraries that will used in this notebook. Okay, what? This is nothing special.
Go up, go up, get path,
Oh, the
go up.
sunlight will not show up in the scene visually, but it is displayed in the hierarchy.
Because I think the visuals are set to off. Okay, look into the hierarchy now. Go down.
Okay.
Yeah.
Scope,
Okay.
lights, distant light, sunlight. Okay, let me understand the code first. So, as usual, we are defining the file path, stage, world. Okay, this is different geoscope. usdgeom.scope. usdgeom.scope.define stage. So, this is the scope we are defining called geometry over here. So, this is the geometry scope. And then we are defining cube inside that, which is getting which is getting defined from geoscope dot get path. So this is gonna be under geometry. And then light scope will be applied to USD geom dot scope. USD geom dot scope define world get path stage, comma world get path append lights. So this is getting defined under lights, I guess. Yep. This is another scope called lights. And then wait. Okay, yes, this is distant lights. And then define a new distant light primitive at path. Okay, so this is the sunlight. And this is getting this is getting scoped inside the lights scope. Sunlight is getting scoped inside the light scope, right?
Hmm.
So, but what is it doing? The sunlight will not show up in the scene visually, but it is displayed in the hierarchy. So, okay, so this is, we can't view it over
Yeah,
here.
right now we
The
are not
sun.
able to see because
Yeah.
the way they have defined it.
Okay. Example two. So this was pretty straightforward. I don't think we need to dive deeper in this. The code is pretty
Yeah.
easy. Setting light properties, we're going to define two new prims, sphere light and distant light, and a set a few properties for them. Okay, define two new prims, sphere light and distant light. So same file path, stage, geom scope, cube is under geom scope. So okay, and then we define a scope prim and stage at light. So a light scope is defined over here, and then we define a sun prim in a stage as child of light scope. So this is going to be scoped under the light scope called sun. Okay. And then another sphere light is going to be scoped under the light scope. So this is going to be under light scope as well. Okay. Configure the distant lights emissive attributes distant lights dot get color attribute. Okay. So now we are setting the local properties of the sun, I guess.
Mm-hmm.
Distant light color red, light intensity. But wait, where is what distant light is equal to this, right? So distant light dot get color attribute set. So this is okay. So we are setting the sun as red over here,
Yeah.
and then distant light get intensity. So
And then
intensity is 120, and lights are XFormable. If not, distant light XForm API equals to GSD geom XForm API distant light raise exception prim not compatible. Okay, so they have made the uh, distant
so
light
if you have to apply
attached
the
to
export
the
formula,
XForm
yeah,
common
and then
API so that it can
non-apply.
be rotated. Distant light XForm API set rotate. So now they are going to set the rotate. But okay, so they did not set the XForm common API specifically over here. How did this become XForm common API?
They were not trying to do any rotation or anything at that point. So initially, they just created a sun at some
Hmm.
distance
Yeah, but
from
my
that.
question is, how was the XForm common API tag attached to the distant light? Because it's just checking here if it is compatible or not. But the thing is, it is going to be compatible if it's setting it to rotation
So
of
so
this.
so so like in Python, you can do an inline function invocation,
Mm-hmm.
right? So if not means that if this doesn't go through, then it's gonna raise an exception, and
Mm-hmm.
if it goes through, it's gonna go it's gonna skip the 21st line, and then it's gonna go directly to 22 since they have defined it over there already.
In 20th line.
Yeah, that is the beauty
So
of
you're
Python.
saying this is going to attach the XForm common API over
Yeah,
here.
yeah. So the
Ah,
thing
okay,
is,
okay, okay, okay.
if it breaks, then it's going to raise an exception over there on line 21
Mm-hmm.
that frame is not compatible because it's gonna. So in Python, if anything breaks, it's gonna
Mm-hmm.
create an exception. So you can basically
Mm-hmm.
catch the exception before
Mm-hmm.
moving on to the code, like before running the code ahead and
Mm-hmm.
figure out okay what is wrong with it. If not, then it goes through. What
Mm-hmm.
happens? Let's say it says if not, like right.
Mm-hmm.
What happens if it is correct? What happens then? So it's gonna go to the line
Got
22
it, got
with
it. Okay, I got it, I got it, I got it. Yeah. And then what is the last part they've done? So they are rotating this. Then sphere light, they're doing, I think, the same thing. They are setting the sphere light dot get color attribute to, I think this is blue, and then intensity is this. And then the same thing they're make attaching the XOM common API, rotating it, and then saving the stage. Okay, and the lights will not show up in the scene visually, but it is displayed in the hierarchy. Okay, I got it. Okay, we are done. This was
Yeah,
pretty easy.
nice. OpenUSD provides a standard way to represent various types of lights in USDC, ensure consistent light behavior across different application and renderers. They support different properties and attributes and advanced features like light filters,
Mm-hmm.
IPS profiles, and linking. Renderers can utilize USD lights and material for accurate lighting calculations, but understanding how to define and control lights within OpenUSD, developers and 3D practitioners can achieve realistic lighting, enhance visual quality, and unlock new possibilities in their projects.
Got it. We are done.
Yeah,
Okay, I think we'll do the quiz later
yeah,
because,
it's
yeah,
getting late. All right,
20
guys. So,
minutes. We did it in 20 minutes. Wow.
so
And
we
we're
have
done with
completed the
two
complete module.
modules. Yeah,
Yeah,
two complete modules are done.
yeah.
We're done with six more. And I think
So,
we'll be able to go through it very fast because we have done the basics really good. And I am getting the code really easily now. Like, I understand this code really easily.
yes, sir.
AI. All right, I'm gonna end the stream. Thanks.
All right.
Oh, okay, भाई consistency.
Yes. चल ठीक है.